All right, welcome to another teaching series. Today I'm going to cover cryptography, but probably it's good to talk about cryptology. So cryptology in general is the actual science of cryptography, and cryptanalysis. So cryptanalysis is the actual changing of plain text to ciphertext, something that you cannot understand, and then so that's cryptography, and cryptanalysis is trying to obviously reverse the process. Again, I'm going to try and use a slide deck as always to try and explain the concept. Uh, People who are afraid of math tend to think cryptography is a little more complicated, but it's not really. Once you can get the basic concepts, it makes it a little easier to understand what is happening, whether it be symmetric, asymmetric, or hashing. But I do my best here to try and explain it. This is basically like chapter 4, although I have another teaching separately on cryptography, or try and look for the video where I address cryptography as it relates to cybersecurity, especially for UAE. But this is my contact information, and normally same thing. That's the little bio that somehow we feel a need to put it in all the slides. There's a copyright missing here for Atawa AI, but it's related. So in this chapter 4, the whole idea is to be able to categorize the primary types of cryptography and the algorithms or the formulas that they use, and be able to describe what we mean by PKI, public key infrastructure, the technologies behind that. So there are two modules in here, module A and B. So let me deal with A and then I'll get to B later on. So here in this module, let's talk about cryptographic principles, symmetric versus asymmetric, and then what is called cryptographic hashing. In general, when we say encryption, it basically means I'm going to take a message, I'm going to apply some kind of algorithm or formula using some kind of key, and then I'm going to create that message for you. And then for you to, that message is now called a ciphertext. For you to be able to decrypt the message, you need that same you need a key to be able to unlock it. I'm going to call it that, right? That's what the encryption really means. But there are different ways of doing it. One older method was what's called a substitution cipher. So, for example, I want to say all gal is divided into 3 parts. That's the message, right? I can use a Caesar cipher or what's called a road 13 cipher. All I just do is just substitute the characters. Like A for the Caesar cipher could be D, for the road 13 could be N. I just change it around. So if you know what I'm doing, it'll be easy for you to get back to the original message. The transposition cipher, here you just, the plain text, you don't do anything with the plain text itself. You just shuffle them around to make it unreadable. So if you see like 3 may keep a secret if 2 of them are dead, that's the word, right? So if I now use what's called a rail fence, I move it around and it now looks like that in this strange way. But the point is that if you know what I'm doing or the key or the process, you can reverse and get the original message, right? So this one is called steganography. Basically, it's hiding something inside something. I can hide a message, especially if you're going on an assignment. I can hide like a coded message inside a music file. So all somebody will see is a music file, but inside the music file, if you know the process to decrypt, you can now get the original message. There's a lot of open source tool like deep sound that you can use to do that. But basically, it's hiding something in plain text that you can see a picture, but inside the picture is a message in there. The different forms, right? But the word digital cryptography, basically, how do I use encryption or cryptographic technology in the digital context? So I can use transport encryption. If I'm sending data across the network, I want to make sure that it's encrypted. So like somebody, like a man in the middle attack, somebody intercepts the message, they will not be able to see the message because it's encrypted. So I'm enforcing confidentiality. Also for storage, which is data at rest. The first one I mentioned, transport, is for data in transit. Just remember that data has 3 states. data at rest, data in transit, and of course, data that is being processed. Memory encryption is there, obfuscation. So now these last three, symmetric, asymmetric, and cryptographic hash, we'll talk about them in detail, but just know that symmetric means I have one key, asymmetric means I have two keys, public and private key, and then hashing, basically, I'm taking a file and I'm doing a one-way process where I get what they call a message digest, or a hash value, and I cannot revert back to the original one. But we'll talk about them in more details in a minute. All right, so you hear the word confusion and diffusion. Confusion basically has to do with making the key very complex, so that if you get only partial key, you cannot be able to decrypt the message. Diffusion just talks about maybe I break up the plain text so that they won't be apparent in the ciphertext. Right? It makes it useless to you if you just get, if you have the known plain text contents, it won't be useful for you in terms of trying to decode the ciphertext. The word randomness and entropy is very important in cryptography as it relates to, if I have randomness, for example, you should not be able to guess, right? It's a repeated process. You have, says it here, like, you can also get by with a cryptographic secure pseudo-random number generator. So in this algorithm, I just find a way to just randomly give you the numbers. And this has been shown to maybe even be effective. But let's talk about the strength of keys. So if you recall that in computers, we talk about bits, zeros and one, and of course, 8 bits make a byte. So if I'm trying to get encrypt a message, for example, it's just telling you that the key length is important, or the strength of the key. So here, 128-bit key, which means 2 to the power of 128, is considered strong encryption. So if you now go up to 256, that means it's even stronger, right? So the longer the key, the question becomes, how do I store the key? So it says key storage is the most obvious problem. So encryption key, I have to keep it somewhere, right? I have to store it somewhere. If it's not in a human readable password. So secure key exchange between parties also is an issue, which we'll talk about later on. But just know that key exchange is, how do I give you the key? How do you know what the key I used? If it's symmetric key, you have something like what's called KDC, key distribution centers. But besides key storage and key exchange, the third issue is key escrow. In other words, if an encryption keys are shared with a third party, how do we escrow it? Right? What's the process for the escrow of the key? So just for this slide, just understand length of the key is important. How do we store the key? How do you exchange the key? And then what about key escrow, right? So remember that the whole idea about encryption is to apply some kind of formula, algorithm. So the algorithm is what you will use to apply to that message to now change it to the ciphertext, right? So if the algorithm has a problem, that means an attacker can exploit that problem or that flaw in the algorithm. So just understand that choosing an encryption method involves thinking about the algorithm, protocol standards that you're going to use. So that's algorithm choice. So for cryptography to work, you need a module, right? So the module is what really implements the algorithm. It could be software, library, something that interfaces with a device, or something that gives you the key in generation. That's the module. So if you're trying to discuss cryptographic basic issues in my class, I will ask you, what are the concerns about cryptography? How do you implement cryptography? What are issues about key exchange, key escrow, key storage? And of course, I'll ask you about the 3 so-called types of cryptography, which is symmetric, asymmetric, and hashing. Even though hashing in its raw sense is not really a cryptographic concept, but we lump them all together because it uses some kind of formulas as algorithm. So now let's talk about symmetric encryption. You know, when you have your Wi-Fi, you use somebody's Wi-Fi password. That's one key, right? That's a symmetric encryption. So you hear the word, they call it also the secret key or private key cryptography, to distinguish between asymmetric, that is two keys, or public key. All right. So remember, symmetric means secret key, private key. Look here, for example, I've got the word 0101100001. I need an encryption key, or if I have the word password, I'm going to encrypt it. How do I do that, right? So I can do it in two ways. Again, I'm talking about symmetric encryption. I can do it two ways. What's called a stream cipher, right? So I'm going to operate, it's similar to like what's called a one-time pad, right? I'm going to be doing one bit at a time. Or block cipher. So I'm going to encrypt plain text in like fixed size blocks, maybe 8 bits, 16 bits, or 32 bits. The point is stream one at a time, block cipher like a chunks at a time. Some of the popular algorithms that we use for symmetric encryption include AES. If you look at your Wi-Fi, you'll see on the bottom like AES 256. In fact, for the US government, AES 256 has been chosen as the, I should say, the normal encryption standard or algorithm that you should use. We've got triple DES, Blowfish, reverse cipher, Salsa 20, right? But most people are going to probably talk about AES, which is the advanced encryption standard. How do they operate? There are different ways. It could be through what's called an electronic code block. Here, all you need to understand here is there is a way to do symmetric encryption. Some of them include what's called hash-based authentication. How do you protect against attacks? But for here, just understand that obviously there's a way to do the encryption, right? So the cryptography itself, there is a guy that did his PhD on cryptography, so just understand that it could be explained in a small way, but it can also be expanded. Just for now, just know symmetric encryption, single key. I can do it with streams or block, and obviously there's a mode of operation. Right. That would be all I need you to know for that. But let's talk about the keys that we use in symmetric or asymmetric encryption. The key is going to have some kind of like a lifetime. It cannot be perpetual, it cannot be forever. So it says it is not a good idea to keep encrypted data with the same key forever. Symmetric cryptography is also called session key cryptography. So now you got another term. Not just are we calling it private key or secret key, you also hear the word session key cryptography. The whole idea is maybe I'm using it for one time, a particular time period, a particular session. But how do I give you the key? You're here, you're in Abu Dhabi, I'm in, say, Abuja, Nigeria, or I'm in LA, and I encrypt something with a symmetric key. I got to get it to you somehow. So there are two ways to exchange the key, either in-band, as in the same process, like say media, or out-of-band exchange. Maybe I email it to you, or I hand deliver it to you somehow. So so we always call it symmetric key has a key exchange problem. That's the reason why you now have things like key distribution center that you will hear later on, right? All right, so just understand that the problem with symmetric key is the exchange of the key. So now we have the second part, asymmetric cryptography, which is now called public key cryptography. Again, remember, symmetric, private key, or session key, or secret key, asymmetric, public key cryptography. So the key tends to be longer. It says this relationship is not strictly linear, but the point is that this is really, really good for tasks that maybe symmetric keys poor at, especially like exchanging of the keys. Just remember the whole idea is a symmetric key has two keys, public and private key, and they go together. Some of the algorithms that we use in asymmetric encryption is the RSA, DSA, elliptic key cryptography, ECC, the more digital version of it, the ECDSA, and then you hear about the Diffie-Hellman that was developed by the two gentlemen, right? This is a good way for exchange of keys. So some people might say, well, Diffie-Hellman is not really an encryption algorithm, but more for a key exchange, but don't worry about that. So just understand that these are the normal popular algorithms. So if you recall, I said data has three states: data in transit, going from point A to point B, data in storage, like what you store on your computer or in the cloud, right? That's called data at rest, right? Data that is stored, data at rest, and then data that is being processed, right? That's the third state. So how do you encrypt data that is being processed? So we now have what's called homomorphic encryption that enables you to work on that data without really having access to the private key. One long time ago, we used to say that you didn't have encryption for data that is being used or data in process. So homomorphic encryption helps us solve that. There's an exercise if you're doing one of the labs for us, or if you're just taking this to review for Security Plus or something else, or just for your knowledge, you don't need to worry about the lab, but it's always good to do some labs. If you're taking the Security Plus exam, you know that it's not just a theory or knowledge or rote learning or regurgitating. You have to be able to do performance-based questions and then perform some labs. So please do the labs if you have access to them, right? All right. So now the third thing I said, you have symmetric, asymmetric, and hashing. So hashing, it says it's a little like public encryption because it uses a one-way function. But the whole idea is that when you cannot go back when you hash something, you cannot go back to find the original text, original value, right? So in hashing, just know these terms. When you have a single digit, you have what they call it check digits. When you have something longer, you have what's called a checksum or message digest. But in general, when we think about hashing, they think about checksum, right, or message digest. That's why we see in a few minutes that so what the algorithms are called message digest, blah, blah, blah. But we'll talk more about how to use hashing in a minute, right? So what are the purposes for hash? The most obvious, one of the great use for that is for integrity of data. I can then verify that something that I sent to you was not corrupted or changed, or the file that you got, because you hash the file, you get a hash value, and then you send me the file along with the hash value. Or if you're using something from GitHub, trying to download something from GitHub or download like Kali Linux, you will see that the actual executable there is stored there with the hash value. So when you download the file, you will hash the file you just downloaded and then compare it to the original hash that was stored there. If it matches, you know that the file is trustworthy, has not been messed with. And of course, you have data identification and key generation. But the third one is password. So we use hashes for password. Most passwords are not stored today in plain text. They hash it, so you don't really have a plain text database. Everything is hashed. So in Linux, you see the etc password, and then of course etc shadow. Same thing with Windows, right? So this is saying NIST says you should always sort or hash your password. So let's talk about that. So sorting and hashing a password means when you enter into a system and you enter your password, I'm going to take a value, add it to that password, and then I'm going to use the word concatenate, and I'm going to hash it, and then I'm going to now store the hashed password and that sort in the system. So next time you log in, you will now retrieve the sort value, add it to the password you entered, and then hash it if it matches, and I'll let you do the system. Peppering is the same concept, right? Hash is stored on the device. Peppering is not stored on that particular node. NIST 2017 guideline for password recommends that a pepper value should be added. So so let's talk about salt for a minute. Salt prevents a single rainbow from table from being from attacking an entire database, while pepper protects individual hashes from being cracked by adding additional secrets. But let me explain the reason why we need to do this. So to crack passwords, you can do what's called like a dictionary attack to look for number of words from the dictionary. You can use brute force attack, keep trying. But now, because passwords are stored in terms of the hash value is what is stored, You have what's called a rainbow table attack. So I just have a bunch of pre-computed hash values and passwords, and I try to use it to crack a password. So salting and peppering tends to prevent that, right? Makes it difficult, make rainbow table attack almost like useless. So I have a lengthy, not a lengthy video, like a 7-minute video on password hashing and cracking on YouTube. This is just briefly, right? Just check it. It says you need to sign in to do that to prevent that you're bot. But this is what you normally will see when you try to get into that. So let me get out of that one. But just know that I have another video that you can check on this, right? All right. So hash-based authentication means how do I get into a system? You have things, ways to authenticate myself. You have what's called a keyed hash message authentication protocol, and you have digital signature. So how a digital signature works is just like me signing normally with a pen, right? You can say that is Alex's Professor Alex's signature. So what you do is if Alice, again, remember Alice and Bob, our analogy, Alice wants to send Bob a message. So Alice has the message, then hashes the message, right, to send to Bob. So when Bob gets the message, he's also going to now hash that message and takes that hash he gets and compares it to the hash from Alice, right? If they match, he knows that obviously its message is trustworthy. But before he can do that, what Alice will normally do is Alice will send that message or sign that message with her own private key. So when Bob gets it on the other side, Bob's going to use Alice's public key to unlock that message. So Bob now knows that that message came from Alice and that message is authentic because the hash value works, right? Again, this is not a lengthy lecture on cryptography, but that's just essentially what a digital signature means, right? You send a message, I sign it with my private key. I also hash the message, and you get those two. When you get on that end, since you have my public key, of course, you cannot have my private key. You have my public key, you use it to unlock my message. Because in asymmetric cryptography, the keys go together. Public and private key go together. If you do something with the private, you have to decrypt on the other end with the public. If you do something with the public, you have to do something on the other end with the private, right? If I'm encrypting with my own private key, when you decrypt with my public key, you know that that message came from me, so it's authentic, right? Because I alone have my private key. On the other hand, if you sent a message with somebody's public key, you encrypted it with public key, the person that has the private key is the only one that can decrypt that message on the other end, which ensures confidentiality. Remember in the CIA trial, you got confidentiality, integrity, and availability. All right, so for purpose of hashing, these are the algorithms, just like we had for symmetric and asymmetric. You have the MD5, SHA-123, and this other two, RIPE MD and Poly 1305. So let me tell you something about MD5 and SHA-1. Those have been what's called deprecated, meaning that they're no longer being used really because they've been cracked because they have some weaknesses. However, we still use them when we're doing forensics, like to hash a file or hash a hard drive. So we use those two still for in forensics analysis. So when I create an image of a file, this is not a forensics class. If you watch my forensics video, we just know that those two are still being used in that sector. But SHA-3 obviously is pretty good. That's I call it third generation, for lack of better explanation. Now, so in storage of passwords, you've got this concept in here. Remember that you don't store the actual plain text of the password, you store the hash value, as I mentioned previously. So for the NTLM, which is new technology LAN manager, for logging on Windows system, both on the networks, right? This is how you store the password and get the bcrypt. All you just need to know here is that hashing is used in passwords. There's a little discussion about blockchain, the importance of cryptography in blockchain because you have digital signatures and cryptographic hashes. These are used to create what is called public ledger. Remember, blockchain works on, well, I don't say remember, but just in case you don't know, it's a distributed ledger, right? So, but just know that there are other distributed ledgers or distributed database. More than you hear about blockchain. Of course, Bitcoin uses blockchain if you're doing a Bitcoin mining. You will hear later on about nonce, but you can explore that later on. But the point here is we're just talking about the importance of hashing and digital signature for blockchain. Here, you talk about DAG here as another ledger besides blockchain. All right, so how do you choose cryptographic technology you want to use? Keeping in mind that you got issues about long key, short key. Long keys tend to be better, but obviously they need more storage. Shorter keys improve performance, but again at the cost of security. The other something called a lower power cryptography doctrine, but the whole idea is whatever you're going to do, know that you're going to have to balance cost versus security. That's what this slide is just telling you, right? All right, so along with that discussion, just know that there are limitations to cryptography. Again, insufficient key length might make it susceptible to cracking. Keys are only one source of entropy in cryptographic scheme. Rotate your key periodically. When you're generating ephemeral as in temporary keys, just understand the issue about key exchanges. How do you exchange the key? If you're going to use if you plan to use a system for a long time, or if you have some confidential data that needs to be valuable or stored for a long time, just think about advanced technology that might compromise that data. The fear is like an example of an advanced technology is quantum computing. People are afraid that quantum computing is going to make many cryptographic algorithms obsolete. But I tend to believe that just like it might make it easier to crack maybe 28-bit, 128-bit encryption, there's also going to be technology to make it also more robust. Just like as we're coming up with things, good things, the bad guys are coming up with bad things, and vice versa. We're always playing a red team, blue team kind of game, or white hat, black hat kind of game, right? Just understand that. So I wouldn't be worried so much. You just say, keep that in mind. All right, so the exercising in creating hashes, I don't have the time to do that, but you can do online hash calculation. Just go to Google and look for online hashing, like a hash, I think hash me or something, and you can just type a text and then hash it and then change the one or two letters in the text, and you see that the hash value is different. Or you take a file, you save the file, you hash it, you get a file hash value. You just maybe add a space or something inside that file. The hash will be different. There are different algorithms. Of course, you have to choose the algorithm you're using for the hashing. Just a few review questions. What type of cryptography is most commonly used for key exchange? Remember, exchanging of key definitely is going to be asymmetric. So I can send it to you using one particular key, and then you can use the other key on the other hand, on the other end, to decrypt it. Password storage, hashing. We'll talk over again. Password storage, hashing. That's the cryptography, right? This one is just more like a memory. RCA was initially designed as a stream cipher. What process gives integrity, meaning that I know that it's not been altered? Authenticity, it came from me, you can trust me. Non-repudiation, I cannot deny it as a legal term, right? Choose the best response. So, classic signature. Remember when I'm saying it's your signature, I'm going to use my private key. That is authentication, authenticity, because only me have my private key. And because I hash, you know that you're going to have integrity. And of course, since I'm sending it, I cannot deny that I sent it. That's where the non-repudiation comes in. That's why B is your signature is the answer, right? So this question basically, if you have 256, 126 different bits, just asking you which of the algorithm you're thinking about, SHA-2 is one that enables you to do that. Now, module 2, again, let's talk about certificate, which people confuse with signature, as in digital certificate. And of course, we'll talk about CAs and then the life cycle. If you go online and you see a padlock on that website, and then you right-click on the website, you will see, maybe if I have time, I will demo this. All right, continuing where we stopped. I was saying when you go online and then you check on a file, you see a padlock, you should be able to know by right-clicking, it will say something about digital certificate is valid, right? So it's telling you this particular website, you can trust it, and you can just check. You'll see what you can check in here. So for digital certificate, basically, it's part of public key, so it's called a public key certificate. Right? You're gonna have one or more signatures that makes you know that it's authentic. The way to do this could be you can self-sign that certificate, or you can use PKI, or use what's called Web of Trust. If Alex trusts John and John trusts Harris, Alex can trust Harris. If you look at the certificate, there are different things about the certificate or what it should contain: version number, serial number, who issued it, the validity, the signature. I will show you a demo in a minute so you can see how a certificate should look like, right? Basically, a certificate should be issued by certificate authority, not just me signing. If it's issued by certificate authority, it just means that private entity is saying, hey, this is Alex, you can trust Alex, right? So basically it's going to take my public key and sign my public key. The types will be domain validation. You can say valid domain. For email, you hear SMIME. I wrote a code, a software is signed, or what's called extensible validation. But how do I get this certificate? How do I get this digital certificate? So normally I will issue what's called a certificate signing request to the certificate authority. I would probably give them my identification information, and they get a public key, and then the process they can now sign and then send the certificate, right? But the certificate is going to have to expire. When it's expired, means I cannot use it anymore, right? Or it could be revoked. Maybe my private key was compromised. So when it's revoked, there are two ways to check that it's been revoked. You have a certificate revocation list. That's the old school one. The modern one is the online certificate status protocol. You just check online and then it can tell you if the certificate is still valid, right? But the certificate has to be stored in one way or the other, right? How do we store that certificate? So it just says you must ensure that the new certificate are not added to the trusted list without your permission. How do you make sure private keys, your own certificate are secret, right? If your private key is secret, your certificate is secret. Otherwise, if somebody discovers your private key, then now that whole thing doesn't work anymore, right? All right, so key archival and recovery, backing up the key. And then, of course, maybe I can have a dedicated hardware storage to store it, right? Or we didn't talk about let me talk about key escrow. Usually, especially, you're going to see a question in a minute. If I want to store it with a third party, I give them to hold for me. That's key escrow, right? So that's the only thing I may have skipped here. Oh, yes, the X.509 standard is how a digital certificate is called the standard for digital certificate. If it's revoked, it's been validated. Hold means it's temporarily invalid but can be reinstated. So let's look at a few questions and I'll show you a demo. Examine PKI certificates, which is a lab exercise, but in case you don't have access to the lab, you can do that, right? All right. What is true of a digital signature but not true of a digital certificate or vice versa? Let's read it again. A digital certificate has a valid starting and an ending date, right? And a digital certificate proves the authenticity of a person or a system, right? So all that apply. Now, remember that the signature provides non-repudiation, correct? And it provides the authenticity of a message. That's why B and C could be confusing. So read that carefully. Extended validation certificate requires a stricter identity verification process when you apply for it. Most modern and flexible, again, OCSP is the more modern way to check the status of a certificate. This question is talking about key escrow because since because of regulatory requirement, your employer demands a copy of all your private key. So it's escrow. That's what this is about. Again, X.509 is for normal certificate from certificate authority, but OpenPGP, is the one that does the web of trust. Just to PGP, which PGP actually means, I think, is pretty good protocol. All right. So this summary, again, contrast the types of cryptography, symmetric, asymmetric, and hashing, no steganography, no difference between certificate and signature, as there is a digital certificate and signature. That's all we really need to know here. And describe that digital certificate is X.509 structure. All right, so next we'll do chapter 5, but let me just, for those who don't have access to the lab environment, I'm just going to show you how to check the, let's share website. Let's go to this YouTube channel. Good. So this is a YouTube channel here, right? This is my video, this is a news channel. But see on here, in old days, if you look on the upper left-hand side, you see what I'm looking at here? Previously, used to have a padlock, but if I click on here, it says connection is secure. About this page in here, this is a YouTube channel. So if I go to this secure, I'm going to see down here, it says certificate is valid. I click on the certificate and it gives me a bunch of stuff about the certificate. Let me go to details. This is issued by Google. But let's go back from into the general. On the general, scroll all the way down here. You see what I'm talking about, the certificate? It says this use SHA-256. This is the long public key. Validity period, September. This one says expiring in about a couple of hours or something. But good, the details in here. What is the version of the certificate? Version 3, serial numbers there. Scroll down again. The public key, the algorithm was used, elliptical curve public key. So you can get a lot of values in here. So you can also export the key for anything that you want to do. All right, so that wraps up the cryptography. And if you have any questions, please send me the questions in the comment line or directly, and I'll be able to answer. If you're a student, you know how to reach me via Canvas or whatever the LMS we're using.